we are talking more about normal distributions. When in 11.3, I kind of introduced normal distributions, right? Normal distributions being the ones that were symmetric, okay? We talked about they could be skewed. We talked about they could be symmetric. The ones that were symmetric were normal distributions. So we are specifically focusing on normal distributions. With that in mind, there's something called the empirical rule that talks about how the data is spread out underneath it. So up here, notice it says the normal distribution has a special property called the empirical rule. The approximate percentage of data values falling in any interval of the range of the data can be determined using just the mean and the standard deviation. Now, a couple of things. First of all, when we're talking population, which is what we're doing right now, the mean can be denoted by, and this is the Greek letter mu. Okay, it looks like a little lowercase u, but it's the Greek letter mu. Okay?
You just say mu?
Mu. And then standard deviation, we talked the other day, is the Greek letter sigma. Okay? And I'm reminding you of this, telling you this, because what might you see in SAVIS or in a given problem or something, you need to, be familiar with these pieces. I know we talked the other day about mean being x bar. Well, when we're in statistics, it could also be mu. Okay? Now, and right here, if you don't know what those are, it makes it hard to understand this image here. But so the middle of a normal distribution is mu, or in other words, that is your mean. So your mean is always going to be right there in the middle of a normal distribution. Each of these lines represents a standard deviation. So like they don't have everyone labeled, but if you look up on mine, the first set of lines is blue. When you go out to those blue lines, that is adding one standard deviation to the right or subtracting one standard deviation to the left. If you wrote it in, it would be doing mu plus sigma, or in other words, the mean plus one standard deviation. To go to the left, it would be the mean minus a standard deviation is what that is. So it's the idea of it's, you're adding or subtracting, you're going one standard deviation away. So what's the second set of lines mean? The second set of lines means you're going two standard deviations away. So it's, I don't know, is that orange, reddish orange line here? But right here it says mu plus 2 sigma. So that's saying the mean plus two standard deviations. So whatever that standard deviation is, adding two increments of it. Over here, the mean minus two standard deviations, so taking the mean, subtracting one, subtracting two standard deviations. And then, of course, what's that mean the next set of lines is? The next set of lines is 3. So this would be the mean plus 3 standard deviations and the mean minus 3 standard deviations. Okay, and that's what we normally talk about, are going out 1, 2, and 3 standard deviations. Okay, that is the normal pieces we talk about. Now, what the empirical rule specifically says. Okay, here in blue. About, it's not a precise, but it's about 68% of all values fall within one standard deviation. So that's saying from one line left of the mean to one line right of the mean. 68% of the data is going to be right there. So a big chunk, notice that's the tallest part of the graph too, is going to be right there. When you go out 2 lines, so when you go out 2 standard deviations, that's the green marking here, 95% of the data. So from here to here is 95% of the data. And then the third piece is that when you go out 3 standard deviations, 99.7% of the information falls there. Now notice my curve is almost touching the number line there, isn't it? So 99.7% of the information, that just leaves 0.3% of the information to be outside of 3 standard deviations. But But these numbers are going to be numbers you're going to want to be familiar with. 68%, 95%, 99.7% are your three numbers there for 1, 2, and 3 standard deviations. Okay? Now, there's a comment here, this rule only applies to normal distributions. So if it's skewed one way or the other, something like that, it doesn't apply. But this applies for normal distributions. Okay? Now, we're going to go set one up and look at some types of questions that you might see with it. So as we look at this population example, an example of an early application of statistics was in the year 1817. A study of chest circumference among a group of Scottish men exhibited an approximately normal distribution. Their chest circumferences ranged from 33 to 48 inches, with a mean chest measurement of 40 inches and a standard deviation of 2 inches. Use the empirical rule to help you understand the distribution of chest circumferences in the study. Okay, a lot to read there. I gave you a blank normal distribution curve, yes? And I did that so we can kind of fill in the numbers on it. So we have those numbers to use to answer our questions. Okay, so what can I fill in on this? What do they tell me here? The mean is 40. Where is my mean on a normal distribution? The mean is in the middle, right? So right here, this line is 40 because it is the mean. Okay, you can also, again, remember that is mu. Looks like a little lowercase u. Okay. Now, as we go out one set of lines, for instance, as we go to the right, what are we doing? We are adding 1 standard deviation as we go to the right. What does that put that line at?
42.
42. Are you guys with her? Basic math here, yes, because we had a mean of 40 and a standard deviation of 2. So each of these lines, I wrote plus 1 standard deviation here, but that is going out 2 more, which is 42. What about if we keep going to the right for the moment? What's that next line?
44.
Okay, it's 44. And that is, since we've gone 2 lines over, that is 2 standard deviations over. So we took 40 and we added 2 not once, but twice. And what's that make the final line here?
46.
46, and that is how many standard deviations above?
3.
That is 3 standard deviations above. Now, just like we went to the positive direction, guess what? We go to the negative direction. So, okay, to the left of the mean, what do we know to the left of the mean? We're going to subtract 2. There's 38. That is 1 standard deviation left. The next one? 36, which is 2 standard deviations left, and 34, which is 3 standard deviations left. Okay. So far, so good with those basics? Okay. If you haven't heard, first hour of my lesson did not go well, so I'm really trying to, hopefully it'll go better this period. We'll see. Okay, so let's look at question A. See if you have any thoughts here. Question A says, what range of chest measurements contains the 68% which fall closest to the mean? Okay. I'm hearing some 38 to 42s. Now, we need explanations because I know I can guarantee I've got some people saying, whoa, whoa, how, why, what? Why 38 to 42? Okay. Our first number up above in the empirical rule is 68%. 1 standard deviation above to 1 below, right here, is about 68% of the data. Are you with me? Okay, it's easy when they give you those obvious numbers. You're not with me. Okay, so I'm using right here our 68, 95, 99.7 rule. 68% says within 1 standard deviation. So that would be 1 standard deviation above, 1 standard deviation below. Now, if you go to our problem, 1 standard deviation above was going 2 up. 1 standard deviation below was going 2 down. Okay, and so 2 up from 40 was 42. 2 down from 40 is 38. So right here, because this is 1 standard deviation, according to the empirical rules, 68% of our data is going to fall between those lines. Okay? So, 68%, and that is plus or minus, I'm going to write 1 sigma, that's 1 standard deviation, right? And what did we say it was? 38 to 42? That was a weird 2. Okay, there we go. 38 to 42 inches. Okay, other questions on that one I should ask?
So we just don't like round, we don't like subtract them to make equal something?
No, because it's what range. So a range being the idea of what's the smallest to largest values in that scenario. Okay. Now, if only they were all this easy. Okay. Let's try B. B asks us, what would you expect the chest measurement to be for the 2.5% of the men with the smallest chest measurements in the population? Any thoughts on this one? Okay, fair answer. Okay, Eli?
It'd be 34 to 36 because, or,
It'd be 33 since it says in the like the paragraph that it starts at 30. It ranges from 33 to 40.
so 33 to 36 roughly.
And why?
Because if you subtract 95 from, or 100 from 95, you'll get 5. And if you divide that by 2 to just get one side, that's 2.5%. It starts at 33, and the next would be 36, so 2.5%.
He's onto something if you followed that at all. Okay. I followed it because I know what I'm the teacher. I know a little bit more what I'm looking for here. So, got more thoughts?
Yeah. The standard deviation, it's 2 standard deviations is 95%, and 3 is 97%. But between the 95% and the 99.7%, well, between 95. Oh my God.
It's hard to explain.
Yeah, it's hard to explain.
Trust me, I think that was part of my issue I had first. As I said, first hour was rough. I'm trying to improve this period. It is. It's rough to explain. I'm going to do my best to get everyone there. Every single one of you, okay? Okay, so they're asking for the smallest 2.5%, right? Now, 1 standard deviation of the data is 68%, correct? Go up to the top of your notes. What's 2 standard deviations? 95, yes? Okay. So what is that saying on here? That's saying from 36 to 44 is 95% of the data, yes? I know some of you are saying, what's that have to do with anything? I promise, just keep with me. Are you okay with the 95%? That is purely just right here. When you go 2 lines out each way, it is 95%. Okay? Now, we're going to do some very basic math. In that, what is 100 minus 95?
5%.
Okay?
Then you divide it by 2.
100 minus 95 is 5. Fair enough? Now, what we're looking at, I'm going to try and do a picture here. If I have 95% going from, what was it?
36 to 44.
36 to 44. 95% is between those two values. What's that leave outside those values? A total of
5%.
5%. Is the mathing?
Okay.
So there's 5% in these two outer pieces. So to the left of 36 and to the right of 44. Now, that 5% is those two pieces together. So what are we going to do? We're going to take that 5% and
Divide it by 2.
split it. Are you with me? If I take 5 and I divide it by 2, I'm at 2.5. So what that's saying is that this piece out here is then 2.5%, and this piece out here is 2.5%. Now, there's the math. 95 plus 2.5 plus 2.5. Am I still at 100%? Because here's what you have to understand. How much data is underneath this curve? It's always going to be 100% every time. So if 95% is in the middle, I've got 5 on my out pieces. If I split it, I put half of it up here, half of it down here. That's putting 2.5 on each end. The question said, what would you expect the chest measurement to be for the 2.5% with the smallest chest measurements? Well, the 2.5% on the smallest end are the values that are less than 36.
Yes.
Okay. Now, I knew they threw out 33 to 36. I would count that as correct. On my answer key, I just have less than 36 inches. And I think I did that. Honestly, I probably forgot the problem said it started at 33. Okay? But do we always have a beginning point? We're not always going to have the chest ranges from 33 to 48. We're not always going to have this information here. We happen to this time. So that's why I could support 33, the lowest piece, to 36. But really what it's saying is it's just anything under 36 inches. What can I answer here? Did I get through to more of you? Yes, no? If there's a question I can answer, please let me try, because once you start seeing it, it's working with numbers, it's not bad. It's getting you guys to see it. Okay. Let's try C. I have something I'll do maybe after we get through A, B, C, D here to maybe help. We'll see. Okay, C. What would you expect to be the smallest and largest chest measurements of the middle 95% of the men?
36.
This one is a somewhat easy question if you've been following what I've been saying. Even if you've only been able to follow half of what I've been saying, I feel like you should be able to figure this one out. It gives that number, 95%. We talked about 95%. That's a number that should sound very familiar to you because it's 68, 95, and then 99.7. So right there, what would you expect smallest and largest chest measurement? So then you're counting out 1, 2 standard deviations. And those values are
36 and 44.
the 36 and 44. Okay, so that is catching on that they use that key value of 95%. 95% takes you out 2 left and 2 right. 2 left is 36 inches. 2 right is 44 inches.
Yeah, and I haven't got a clue how to do D, so.
I will say, A and C are the easier ones. I'm hoping that, are we kind of at least following on A and C?
D.
Okay? D is a little more difficult, kind of like B was. You have to break it down, but we'll get there.
Oh, yeah. Never mind, I got it.
I got it.
Now, I will say, there's probably a couple of different ways we could talk about D. So I'll be interested to hear what ways you start to see it. Okay? D asks us, what would you expect to be the measurements of the 16% of the men with the largest chest in the population? Okay? Now, we can kind of think of this like B. Okay, there is a similarity here, just different placements. Jack, is your hand up?
Yeah, could it be greater than 43?
Mm-hmm.
Could it be what?
43 and greater?
Not 43,
Anything greater than 42.
because I don't have a 43 on here. It's going to need to end up being numbers listed here that we're going to reference.
Okay, well, 42.
Okay? I could support 42. Okay? Now, do you have an explanation for me?
Well, I was going to go with 43 because it's like a bigger percentage gap for I don't know how to explain it.
So you were kind of guesstimating, I'm guessing.
No, well, 43 is like, I have an explanation, I just don't know how to explain it.
Okay.
I think I can explain it.
I've been caught in that position today. I don't know how to explain myself. I get it. Okay. Okay. What are you going to say, Savannah?
So basically what I did was I realized that it was 16% of the largest. So if you take the 16% on the largest, you would add a 16% for the smallest, and that gets you 32. And then I subtracted 100 from 32, and that got me 68. So then I knew that it was everything that was larger than the first standard deviation.
Okay.
And so then that's how I got my 42. Anything larger than 42.
Okay. Not tracking. Again, this is kind of like last time. I'm tracking because I know
Yeah,
where I'm going. I'm understanding,
what she said.
were you kind of tracking with that?
Yeah.
Okay. Okay. On B. Go back to B with me for a moment. Okay. B, we were looking for 2.5%. 2.5%, if we work backwards, was half of 5%. 5% was the extra when you took out the middle 95%. Okay. Now, if we treat this one the same way, 16% is the top. We're looking for the largest, right? Is the top piece. So if there's 16% up top, that means there's
16% on bottom.
there's also a 16% that equals out on bottom. Kind of like earlier, it was the 2.5 to 2.5. Now, when I put 16 and 16 together, that is
32.
32. When I take 32 from 100, that puts me at 68. Is 68 a number we know?
Yeah.
68% is one of our key numbers. Now, let me walk you through it forwards. Okay? 100 minus 68. Let's go there first. What is 100 minus 68?
32.
32. Basic math, yes? The math we're doing is really just basic math. Now, so think about this. If I have 68% in the middle going from, what was it? Oops, nope.
38 to 42.
38 to 42. Okay, 68% of data goes from 38 to 42. Now, That leaves 32% to be where?
On the outside.
32% to be on the outsides of those. But that 32% is,
Split it
it has to be split, right? Because some of it goes down low, some of it goes down high. Goes down high? What? Up high. Okay, so 32 divided by 2 is 16. So that means that to the right of 42 is going to be 16%. And to the left of 38 is going to be 16%. The thing is, this is really hard to write out. It just is. So now,
Maybe you shouldn't have to teach it there.
tell my standards that. Keep with me. If I take the 16, the 68, and the 16, does that add up to 100% of my data? Okay, it does. Okay, the calculator will verify. Our question was, what would you expect the measurements of the 16% of the men with the largest chest to be? So where is the largest 16? Right here. And where is that? To the right of 42. And so thus my answer is, I have it written as 42 inches or greater. Okay. Now, to kind of, I know Jack threw out a 43 number, okay? The way these percents are designed, they're always going to hit right on my standard deviations, okay? And so that's why it's going to land on 42 or 44, but not in the middle of it. Okay? Other thoughts of ways to explain that to your peers? More explanations needed? I don't know. I'm not 100%, I'm not convinced everyone's with me.
How did you do it?
We're so with me. Some of you are right there, you got it. Some of you are borderline.
How do you know it's the second 16 and not the first 16?
It's the largest.
Because it wanted the 16% of the men with the largest chest. So now, what does that mean is below 38? Below 38 are the men, the 16% of the men, the smallest 16% of the men.
So would that be like 38 or less?
That would be 38 or less.
Good job, all three.
Okay. I'm trying to get you guys to put it all together. Okay. One thing we did first hour, and I don't know if it was a pro or a con, we also took this and divided each of the pieces up. And I don't know if that was helpful or not helpful, but the idea that, okay, if 38 to 42 is 68%, what does that put in each piece? Well, that puts 34% in each piece, yes? And that's not true on just this problem. That's true on
The next one too.
all of them. So are you guys with me that each of those would be 34? Because 34 and 34 is 68. Now, what's interesting is, what are these next two pieces?
13.5.
They're the difference between 95 and 68, yes? 95 minus 68 is
27.
27. If you take 27 and divide by 2, because here's the deal, 27 is these two pieces together, so what are they individually? 13 and a half. So you've got 13.5% and 13.5% there. Could you keep going with that?
No.
Yes. What's 3 standard deviations? We didn't need it on this problem, but what's 3 standard deviations? What's the percent?
2.5.
From 34 to 46 is 99.7% of the data, right? Now, that means that from 44 and 36 out is 2.5, but if we break it into the pieces, 99.7 minus 95 is 4.7. 4.7 divided by 2 is 2.35%. So what we're saying right here, that's 2.35. That's 2.35. What's out past the third standard deviation?
0.3.
If my data includes 100% of the data, 100 minus the 99.7 is 0.3. 0.3 divided by 2 is 0.15. So this is 0.15% is out past that third standard deviation.
That actually makes the back one easier.
Yeah.
Yeah, it makes the second
Makes the next one easier? Okay. Now, those percents I just wrote in light blue are true every normal distribution curve ever. Okay? Every single time. Now, with that in mind, 2.35 and 0.15. Guess what? Those are the 2.5% we talked in example B. Okay? The 16, if you add 13 and a half, 2.35 and 0.15, it adds up to be this 16% we talked in example D. Okay, so these percents could add in multiple different ways and support everything we've just done. Okay? Okay. Ready for the next one? Ready as it's going to get. Okay. Recent SAT scores for college-bound seniors are normally distributed with mean score 508 and standard deviation 121. How does the empirical rule help you understand the performances of individual students? Now, technically, we could just go into the questions. However, I left you a blank normal distribution curve, didn't I? And my suggestion is we fill in information on it. Okay? What's in the middle?
508.
Because 508 is the mean. You guys with me there? Now, what is 1 to the right of 508?
Oh, yeah.
Why 629?
That's plus 121.
Because you're going 1 standard deviation over, and 508 plus 121 is 629. Let's keep going right. What's the next line?
750.
Because
It's 2 standard deviations.
2 standard deviations over, just add 121 to the last one, yes? You said 750? What's 3 standard deviations out?
877.
Because 750 plus 121 is 871. Not that you have to write that work down, but is it helpful for some maybe? Some people may look at this and say, I have no idea where these numbers came from. What am I going to do on the left? Yeah. To get that first line, you're going to take 508 and subtract your standard deviation. So 508 minus 121 is?
387.
387. Then you're going to subtract the second one. 387 minus 121 is 266. And then to get to the third standard deviation, 266 minus 121 is 145. And you guys know what we did, right? We just went 1 standard deviation to the right, 2 standard deviations, 3 standard deviations to the right. And then we did the same thing to the left. We went 1 standard deviation left, 2 standard deviations left, and 3 standard deviations left. Okay. Having those numbers set in is going to make doing the actual problems easier, I promise. Okay, we ready to talk A? What proportion of students received scores between 387 and 629? Is it coincidence that 387 and 629 are two of the numbers we just came up with? Not at all, is it? Notice 387 is one left of the mean, 508. 629 is one right. So right there, that is one standard deviation to the left, and that is one standard deviation to the right. What is our rule for one standard deviation out?
68%.
The 68% you threw at me. You're understanding the basics if you can at least see the 68%. Okay? You with me? Okay. What proportion of students receive scores greater than 387?
84.15.
Disagree.
Why
I disagree with the decimal part
Why
there.
wouldn't it be? I
Yeah,
just
no,
think
it'd
before,
be-
I used the last one because we figured out that outside of that 68 is the
16,
point, so
Yeah,
I
it
used.
would be the 0.15.
But,
It's greater than
Because it's greater
387.
than it's.
So you have to go all the way to 100%.
right,
So it would be the 84% that you would get if you went just to 871 and plus the point.
no, the 84% takes you past 871. It takes everything.
I was just saying if we figured out last time, it was 16, so I got the 68 versus 16.
You just like take the percentage 68 divided by 2 and divided by 2 again and just add that to 68.
I only divided it by 2 once, but,
Well,
well, I guess it depends how we're looking at this. Okay. Okay. There's multiple ways you can look at this, and that's, you know, debating what way I want to go here. I'm trying, how did most of you guys go? So you kind of looked at, okay, let me ask this question. What do we know? 508 is your mean. What's that mean? How much of the data is to the left of the mean? How much is to the right of the mean?
50%.
That's a 50% dividing point, yes? Okay, so if that is 50% to the right of 508, okay, so if right there, we know there is 50% to the right of 508. What else do we need to know? We need to know how much is between 387 and 508, yes? Now, what is obvious to me, and I think this is where maybe Jack was just going, what do we know from 387 to 629?
68%.
That's 68%, yes? If that's 68%, what do you know about each of those pieces?
34.
Can we agree that they're each 34? Right? Because basic math says 68 divided by 2 is 34%. So if we're saying that each of those pieces is 34%, what is between 387 and 508? 34%. So it's the idea that like each of these are 34, yes? And we figured this on the front page. But we also just talked about that from here, from 508 over is 50%. So what could you do here? Add the two. So the 50% plus 34%, which is indeed 84%. Could you go back to this right here and just add all these numbers? 34, 34, 13.5, 2.35, 0.15? You could. those would also add up to 84. Okay? Okay. The next question is easy if you looked at it. Did you guys look at C before you started packing up?
No.
95%.
What proportion are earned between 266 and 750? Where are 266 and 750?
The second.
They are at the second lines, right? And the second lines, that's 2 standard deviations left, 2 standard deviations right, so that is
95%.
95%. We like those questions, don't we? 266 to 629,
81.5, I think is what I got. Yeah.
it is 81.5. We'll have to talk tomorrow. Remind me.
Have a good day.
Yep, 81.5. Because you can look at 68% there, and I think that was 13.5 over there. So yeah, we'll talk about that one tomorrow.